In part A, we determine the velocity and acceleration of the rock. So first, let's determine the velocity of the rock. And this is given by the derivative of the height of the position function. So since s of t represents the height, we say that the velocity is equal to s prime of t. S prime of t is the first derivative of the height function s of t. So, and this equals, we have to find the derivative of s of t, that is 7 plus this is 48t minus 0.8 t square. So here when we find the derivative, we find the derivative of each of the terms inside the brackets. So we can write down this as a derivative of 7 plus derivative of 48t minus derivative of 0.8 t square. The derivative of 7, which is a constant, is 0. So this becomes 0. We can put this as 0 plus derivative of 48t. When we find the derivative of 48t, we factor the constant 48 out of the derivative and find only the derivative of t. So therefore this becomes 48 times of derivative of t alone. And similarly, when we find the derivative of 0.8 t square, we factor out the zero point 0.8 and multiply with only the derivative of t square. So we write like this. Now let's find the derivative of t. The derivative of t is 1. So therefore this becomes 48 times of 1 minus zero point 0.8 times of derivative of t square. When we find the derivative using the power rule, we figure out that this is equivalent to 2t, because we put the 2 in front and reduce the power 2 by 1. That is 2 minus 1 is 1. So therefore this becomes 2t power 1, and which itself is 2t. So this can be simplified, and this equals 48 minus of zero point 0.8 times of 2 is 1.6, and then we have t. So this is the expression for the velocity function, that is s prime of t. Now let's find the acceleration function, that is acceleration of the rock is defined as the second derivative of the height function, or it is the first derivative of the velocity function. This represents velocity. I write down here. So basically acceleration, that is represented as s double prime of t. This equals the derivative of the velocity function, which is s prime of t. So let's calculate this. That is, this is d by dt of s prime of t. Let me replace that expression, which is 48 minus of 1.60. So once again, when we find the expressions inside the brackets, we find the derivative of each of the terms. So the derivative of 48 is 0. So therefore this becomes 0. And then we have negative 1.6 t, which we have to find the derivative. So once again, we can factor the 1.6 and find only the derivative of t. So the derivative of t is, according to the power rule, it is 1. So basically the acceleration function is negative 1.6. Let's answer part B. That is, here we have to determine the time to reach maximum height. So for this, I have drawn the approximate graph of the height function, that is s of t. So this is the graph of the s of t, which represents the height of the rock at time t. And so clearly we can see that this graph is a parabola opening downwards. So it opens downwards like this, and this point is the point where it reaches the maximum height. So according to the calculus, we say that this is a local maximum of the function, or we also say this as a relative maximum. So at local or relative maximum, the graph of the derivative function will be 0. That is the derivative of this s of t, which is s prime of t, and this is nothing but the velocity function. So to determine the maximum height, or the time it reaches the maximum height, we basically have to set up the velocity equation equals 0, because at the local maximum, uh, the velocity function is 0. So we consider the velocity function, which is 48 minus of 1.60. We set this equal to 0. So therefore we can solve for t from this equation. So I add up 1.60 to both sides. So therefore I get 48 equals 1.60. Now I divide both sides by 1.6. So this becomes 48 over 1.6 equals t. And this equals, we plug this into the calculator, 48 divided by 1.6 is 30. So we say that at time t equal to 30 seconds, the rock reaches the maximum height. And we put the unit of time, which is seconds. So this answers this question.